Welcome back to yet another session. Here we want to proceed further. Last class where we stopped was with regards to slice selection. So now that we have selected a slice and this is the sequence diagram that we represent, right? So you had the excitation and during the excitation you enabled a gradient and we enabled for convention we said this is the Z gradient which will give you axial slices. And when you do Z slice, the signal is still not coherent in that volume, right? Because it is all diffused, defaced, because there is a difference from one side of the thickness to the other side of the thickness. There is a different frequencies and therefore different grade field strength and therefore different frequencies, right? And therefore you won't get coherent signal. So because of that, we apply what is called as a refocusing gradient, which is applied for a short duration, tau p by 2. And immediately when you do that, the slow tries to become fast, the fast tries to become slow, and therefore in that period, there is a point where all of them will come together, which is giving you the signal. And we recorded the signal, we denoted it as analog to digital converter. So essentially this is how we denoted as our readout signal. We are measuring this signal after this sequence, correct? But what we need to know is, okay, I know how to build a signal from a particular slice thickness. Now, what is it that I'm measuring? What is the meaning of what I'm measuring? I know the signal is going to come from this volume. First is understanding the mathematics and the intuitive meaning behind the signal. And once we understand the intuitive meaning behind the signal, our aim is to actually see the distribution. We want to see the image, that is x comma y of wherever the signal is coming from. Not that the signal is coming from this slice thickness volume. That is not important for us. So first we understand the basic model. This is a very powerful concept. So please pay attention to this. If you understand this, which is the most difficult part to understand in an MRI, the rest of it with time you will be able to enjoy your own interpretation and beauty. What we know from before is the signal comes from the transverse component MXY. When this transverse component spins, you have a coil, you get the free induction decay voltage signal, correct? So our S of t, the signal that we are receiving, is coming from MXY with the t from the whole slice. So the whole slice is contributing, whichever got excited. So your S of t is a net from this whole slice of your MXY component from different locations, right? So what is this MXY? The MXY is the transverse component. What will happen just after your excitation is off, right? You pushed it. This MXY is going to change with the time. How is it going to change with the time? It is going to decay. More specifically, it is going to decay with some time constant, which we called as T2, or more precisely T2 star and T2, right? That we will make a distinction. So your MXY of T, we know is MXY 0 plus. What is this 0 plus? Oh, this is just after you start, after you pushed, just after you start to receive the signal, 0 plus, right? What is that? That is going to be your M naught. M naught is your M naught sin alpha. If alpha is 90 degree, you are pushed to the equilibrium value to the floor. That is your starting point, and the starting point gets to reduce exponentially with a time constant T2 or T2 star. So this M0XY is nothing but your first model we did, B naught gamma square. Essentially it is related to your proton density. So now quickly you see the transition. The basic signal here, the proton density contributed from proton density, right, is falling on the floor, and that is the starting value. That is decaying with the time with some time constant. So what you are measuring S of t is nothing but every component that is coming from this complete slice. Okay. Of course, the M of t, we should be careful. This is correct. Like I keep saying, T2, we have put it for purposes of explanation and going forward. But do recognize that technically this is T2 star. The rapid defacing happens due to T2 star. Remember, we dot T2 when we did the spin echo, right? When we did the spin echo, we said we could get the T2 decay, otherwise it is T2 star decay. So if you are just measuring the free induction decay, then you should replace the equation with T2 star. If you are doing spin echo, then it is more appropriate to use T2. So for ease of following the concepts, we'll go with T2, but do recognize there is a subtle difference between whether you are going to use T2 or T2 star, or the signal that you get is weighted based on T2 or T2 star, depending on whether you are measuring the free induction decay or you are measuring the echo. Okay, so that is a subtle difference that keep in mind. But essentially we see what we are seeing here is a signal is from the whole volume, right? Measured signal is modeled like this. This is your B naught, right? So from your omega naught comes from your B naught. So you can write it like this. So I will recognize f of x comma y to be mxy0 plus the starting value exponential. This is my signal. Just I want to write it in signal form so that you start to recognize in the generic signal form of f of xy, right? So of course this is approximately equal to mxy0 plus if you consider a time instant that is much shorter than your t2, right? Very straightforward. But what is important for us is to recognize that this is nothing but your specific density. What is mxy0 plus? Right, in the last equation in the previous slide we show it is all that constants are there, then you have your proton density. So your signal in some sense is related to your effective spin density, whatever you are measuring here, right? Of course I will first not work with S of t. Almost all of the instrumentation, all of the MRI processing, signal acquisition and processing works with demodulated signal. Okay, so we'll use the baseband. So we will use S of t instead of using S of t, which has e power minus omega t. There's a high frequency. We will use S of t as S of t into e power. So essentially, you're removing the omega naught, or you're moving it, or you're demodulating it. So you have only baseband. So we'll manipulate this and call this as the baseband signal that we are going to play with. Baseband signal is nothing but f of xy dx. Okay, so we'll interpret this baseband signal going forward. So we know this mxy is proportional to your PD, and MRI signals, therefore what we are doing are mainly influenced by PD in the signal equation that we have shown. Okay, so what does this say? Why is this effort? What is the intuition behind this? Oh, this is very common sense, right? If I have a larger volume, I will have more signal. If I have less volume, like your slice thickness now, when you have a bigger slice thickness, I will have more volume, like imaging plane times the delta z. I will have more signal. Whatever I am measuring, we have not gone to that, which will go. That mxy that you are measuring, the S of t that you are reading out, will be high if you have a larger thickness. It will be low if you have thinner slice. That's what this intuition tells, right? So naturally you want good signal, right? Therefore you're not going to have ideally thin, infinitesimally small imaging plane. So it's a trade-off with already the trade-off with one approximation that we have done, one slice thickness direction that we have done. The story doesn't end here. Okay, we will have some slice thickness that gives us the best signal possible, or signal level that is acceptable to us, and the resolution is acceptable to us. Now what we need to do? He still says it is coming from this volume. I need to know where it is coming from this volume. That is the x comma y. So for that we do spatial encoding. Following the selective excitation, all spins, right, only within the selected slice is excited. So the next signal that you get is from all the spins within this volume. Now I have to recognize within this plane where is this contribution coming from. To do this, to form an image, we need a way to determine the spatial distribution of the signal within this slice, right? How do we do that? We'll again do the same. We have the gradients in the two other directions, right? The x and y. This is the imaging plane xy. So what we will do is, after you apply the excitation, do the RF selection, we'll apply, that time we applied only gradient z. Gx and Gy were 0. Now what we will do, we will make G0 0, right? I mean G is at 0. So you have selected the slice, that is what is giving signal. During the signal readout, we will enable gradients in the other two directions. If we are able to do that, then we may be able to say which location within xy corresponds to which frequency, and therefore we know from the recorded signal where it came from, right? So this is how generally it works. So we'll go one step at a time. So 3D volume we collapsed to a slicer. Within the slice we need to now do first row and then column. Eventually image is a matrix x comma y, right? So we have reduced it to xy now. We need to now use x and y gradients to our advantage and separate x comma y. So how will we do that is, first within this plane we will break it into rows, and within the rows we will break it into column, right? That's another way of thinking about it. So if a gradient is applied during the data acquisition, then the signal contribution from spins from different points along the directions of gradients will have different frequency. This is what we exploited in Z direction. We can exploit the same thing in whichever direction we want, right? If you apply a gradient along the gradient axis, the frequencies are different. So if you record the net signal, which is a combination of each of these signals, then you know where it came from. So this is known as frequency encoding, since the location of the spins encoded is the frequency of their emitted signal. Okay, so first we'll go, if you do everything at once it will be confusing. So what we will do is, first we will do one of the directions. Typically x is called as the readout direction. So we can apply a gradient in the x direction. What will happen if I apply a x gradient? Then along the x direction there is going to be a change in field strength, and therefore there is going to be a change in frequency along the x direction. What I am recording is still the net sum, but here I know signals that are coming from along the x direction will have different frequencies. So what I am going to capture is going to have multiple frequencies, but I know which frequency came from which x. That much I know, right? That is the frequency encoding direction. So to look at this slice, so we have selected a slice. If I have x gradient, right, the arrow mark is changing, right? That is, field strength is changing in only x direction. Then you notice that within this volume, I know along the x direction, right, along the x direction, everything, the frequency is going to change because your B is changing. So you will have, on one end you will have lower frequency, the other end you will have faster frequencies. The lambda frequency increases from left to right because your B naught increases from left to right. So the frequency thus provides a label to identify the spin location. So what I can say from here is, not only this signal is coming from this excited slice, I can also, the recorded signal also has information of at least one another direction. I should be able to tease out that it came from this x location, x location. I still have to do the y location, right, x comma y, but at least here I will be able to say within a slice all of x. So I have sliced it along x in some sense, if you think about it. Okay, so we have, so the signal that you are recording has this encoded signal, right, information. How do I decode that information? For that we need to understand the signal little more detail, the mathematics of the signal that we modeled, right? We should start to see it not just as a mathematical equation, but also as the physics of the operation that we are doing. So what we have done is, in one direction, x direction, we have applied a gradient. So we know the signal that you are recording is going to have multiple frequencies, and we know each of this frequency is changing along the x direction, right? So we will write this in our right as in, now put the sequence diagram to explain this. This we know RF, this is a slice selection, this is a refocusing. So your signal started to appear, right, when you pushed it on the floor. But while it is on the floor, just after you pushed it, you are encoding, you are owning the X gradient, Gx. That means you have encoded the frequency and you are recording the signal during the readout when Gx is on. So the signal that you have recorded is going to have the signal that you have recorded is going to have information. In our sense, it is going to have information which is going to be composed of different frequency content, right? Because you have a gradient on in X direction. So each location along the X direction is experiencing different Larmor frequency. You are doing net sum, correct? And therefore you are going to have the recorded signal is going to have all the frequency components, right? We'll look at it a little more. So when you're going to decode the signal information, the frequency encoding gradient, right, makes it possible because it spins different locations in X are going to have different frequencies. So let's read the English form of the signal that we are acquiring and then look at it from physics and then go into the mathematical understanding of it. So what we are saying in other words is the net signal, right, is now consisting of sum of contributions of different frequencies. Why is it different frequencies? Because you have X gradient. So each of which originates at different position along the direction of frequency encoding gradient, which is Gx in this direction. Is any mathematical concept, meaning of any mathematical concept comes in by reading, understanding the meaning here. When you talk about frequency contribution, you're going to have contributions of different frequency. What does it sound? It sounds very similar to what you talk about frequency spectra, right? In other words, the spatial distribution is given by the frequency spectra of the signal. I have contributions of different frequencies. What is that? That is your frequency spectra. So the frequency spectra contains information about the spatial distribution. This is very powerful. Okay. So now we understand this meaning. So the signal that we have captured is having contribution from different frequency components. So we get a feeling that whatever we are capturing is actually the frequency spectrum. But let's put the equation and see whether we recognize that. Okay. So clearly that means there should be some relationship between the spatial distribution and the Fourier transform, right, of the signal time course that we are doing. So we'll see the signal that we have and see whether we are able to appreciate the meaning of the signal. So you have Larmor frequency along the X direction. So this is nothing. Our Larmor frequency is changing because I have only gradient in X direction. If I write out my signal, the baseband of the signal is nothing but f of x comma y e of, I've just expanded this, right? That the frequency that was there in the previous slide when we wrote the signal equation, I'm expanding it using this, right? So if I do that, I get e power minus j gamma gx x t dx dy. Now when you look at it, it should be strangely similar to a standard formulation that we know. And what is that? A 2D Fourier transform. Recall when we did the first few classes, right? 2D Fourier transform f of u comma v is fxy e power minus 2 pi ux vx ux plus vy, right? U and v being the frequency directions of x and y, right? So now you clearly start to see something that was weird at beginning, but we know the mathematics. It's just that our mind is difficult to comprehend because we are always used to looking at Fourier transform as you acquire the signal in time domain and then you transfer it to frequency domain. Now I am saying we are acquiring S of t, but that S of t itself looks very similar to the Fourier transform. So what is it that we are recording, right? So your S of t is nothing but Fourier transform of f of xy, right? It's a Fourier transform of f of xy. F of u is, you recognize the variable, u is gamma gxt, v is 0, right, in this equation. So when you compare S0 of t and the standard 2D Fourier transform of f of x comma y, you recognize S0 of t that you have measured is nothing but is actually a Fourier transform with frequency components u and v. Mind-boggling, right? So what I have said, what we have realized now, that we are not actually measuring the time domain. Even though we plotted the free induction decay in time, it turns out that the signal that you are measuring is nothing but Fourier transform, the Fourier transform of the object f of x comma y. So from what we have measured so far, if you have to put it in the space of u and v, you have measured this. Fantastic, right? Now you recall something similar we did when we did 2D CT. You had a detector array, a famous theorem, right? Fourier slice theorem. You have a 2D, you have a detector array, you measure the signal, take the Fourier transform. The Fourier slice theorem said this is one slice in the 2D Fourier transform of the object. So then our entire concept changed. So then we said, oh, why don't we acquire several projections and therefore populate the Fourier space. Once you have the Fourier space of the object, that is the Fourier transform of the object, I can get the object as the inverse Fourier transform. So we acquired different views, acquired different projections, took the Fourier transform and constructed the Fourier space, Fourier transform of the object, and then obtained the object as inverse. Here what we are seeing is, I am actually measuring directly the Fourier transform, the Fourier space of the object. I am actually measuring the 2D Fourier transform space of the object f of x comma y. Fantastic. So now it tells you that if I want to acquire the MRI signal, image MRI, then if I can repeat this experiment and cover the whole space, then I can take inverse Fourier transform and I will have the object. And the object in this case will be proton density, where it is coming from, right? Clear? So fantastic. So let's see how, if we have to do all this, we need to be able to cover different strategies we can use to cover. So first is, our objective is still locating the voxel in the slice. Your FID gives sum of signals from all the voxels. So you are getting one from the whole slice. Now our objective is to separate the contributions from different voxels. So what we have seen now is, if I apply x gradient, I can separate it out, at least the x. So if I can apply y gradient, then I may be able to also separate the y gradient. Right? Therefore I can get my f of x comma y. First we can do this in a several ways. So instead of scanning the spatial location, we are actually acquiring the Fourier transform space of the object. Once we get that, we can do the inverse Fourier transform and get the object itself. So how can you scan the Fourier space? You can scan it with the different strategies. One is polar scanning, where you essentially rotate. Right? We saw a U here in the previous sequence. By applying one particular gradient Gx, we got along this. So if I have to repeat this experiment multiple times, perhaps I can repeat it with different values so I can manipulate. So that is one polar scanning. Other way to cover the Fourier space would be, I can do rectilinear scanning, right? So we'll go into each of them with little more detail as to how do we saw how you start at the origin and cover positive U, right? We saw that. Now how do we execute this strategy? How do we execute this strategy? We need to understand. So to execute this strategy, I need to be able to move along Uy at different angles. To execute this strategy, now I know here, to execute this strategy, I might be able to not start from the origin. I should be able to start from negative axis and then move left to right. Not only that, and I should be able to move like parallel in the V direction also. Right now I know only how to start at the origin and acquire data. Your gamma gxt gives you highest frequency. I'll stop here. So I can start with 0. I start with gamma gxt ts, right? Acquisition time, highest frequency. But I need to have a way to start on the negative axis. Not only that, I should be able to do that at different V. How do we do that, right? So there are several strategies. Let's start with polar scanning. When you do polar scanning, it's straightforward. We put the timing equation, like the pulse sequence diagram, and it will become very vivid. So this is nothing new. You apply the RF pulse in this, and then you do the slice selection. You do the slice selection with a Z gradient. I could have marked this as Z gradient, but it is given that with the convention that we are following, Z gradient is used for slice selection, right? Slice selection, refocusing, you make a signal come out. When the signal is coming out, if I apply Gx and Gy, right, I can move this vector. So when I had only Gx, no Gy, it was lying here at 0 degree. If I want some other theta, I will have to apply Gy. Gx and Gy is in my control, so I can get any theta I want. I can repeat this experiment. I am reading the signal. The signal is now a contribution that is encoded with Gx and Gy. So I know where the signal is coming from. If I repeat this experiment several times with different Gx and Gy, I may be able to cover the whole space. Of course, the only thing is each time, in order to come to the origin, you will have to wait. You put one sequence, you get one thing, you wait so that the signal comes back, and then you repeat the experiment. Okay. Highest frequency will be, your frequency axis will be gamma Gxt, gamma Gyt. The highest frequency will be until how much ever you are recording. You are recording it over Ts. So gamma Gxts, gamma Gyts would be your highest frequency that you have recorded in the UV space. So you repeat this with the different Gx and Gy value, you can cover the entire space. Fantastic, right? Simple. Once you have the entire space, take inverse Fourier transform, we will get the image. So job done. Okay. So now what we need to do is, we need to have a way to do two things. If you have to do rectilinear, you have to go to the negative axis and you have to move along V. Okay, so for rectilinear scanning, you need to move to negative axis, and we will use a concept called gradient echo for that. Likewise, we need to move along the V position, right? There we will call it what is called as phase encoding. Okay. So let's start to understand how do you gradient echo, or how do you move the starting point to the negative U axis. Everything is same. You apply the signal, you do the slice selection, you do refocusing, you get some signal. But notice that I am also applying a gradient x. The only thing is I am applying a negative gradient x. You can apply positive gradient or negative gradient, right? If Gx, you can apply minus Gx or plus Gx. Just the direction. But notice an important point. I am applying a negative Gx. Okay. The signal is there. So I can also encode this, right? The signal is there. The free induction decay is there. I have a negative gradient, but I am not recording the signal at all. I am not interested in that signal. What I am interested is after I apply the negative x gradient, I switch to positive x gradient. Remember cunningly how we did this here. We switched the gradients here. Why did we do that? Because there was a slow end, there was a fast end, right, within the slice. When we switched the gradient, the slow became fast, fast became slow, and therefore the signal started to add up. Very similar. So I have a signal, free induction decay signal, but I'm not recording it. Instead, the gradient is switched. The x gradient is switched. When I make it opposite polarity, the signal now which was dying starts to build up again. The slow guy tries to become fast, the fast guy tries to become slow, and therefore you are going to have high signal add up, and then of course it will die down. You are recording actually the echo signal, not the original signal, and therefore this is called as echo signal. Not only that, this echo is coming because of the gradient. The signal is coming, the echo of the signal is coming from the gradient, which is what you are recording, and therefore it is called as gradient echo. Remember, distinguish this from the spin echo that we did. Fundamental difference. The echo, there also it was the same idea, right? It was dephasing, you made it refacing, you got the echo signal, so we called it echo. but that rephasing started because of applying RF excitation pulse that flipped to 180 degrees. Clear? So your dephasing was happening because of spin-spin interaction. Okay. Whereas here the echo is coming because I am changing the magnetic field, not because of spin-spin interaction. I am actually changing the magnetic field. Remember, your T2 star was due to change in magnetic field. Your T2 is due to spin-spin interaction. So here I am deliberately changing the magnetic field so that I make it in phase. Okay. So this is also an echo, but this is coming from gradient echo. So it is T2 star decay. That is the fundamental difference between spin echo and gradient echo. Both are echo, but the spin echo you get it from applying RF excitation pulse, whereas gradient echo you get because of switch in gradient. Therefore, fundamentally the decay constant in gradient echo is due to T2 star, changes due to signal loss due to change in magnetic field strength, right? That is T2 star. Whereas your spin echo is based on T2. Very fundamental concept, but easy to get confused. But I hope you listen to this lecture few times and get a feel for it. So what does this do? This essentially has pushed to A. This is no big deal. Actually think about this. When I applied this negative X gradient, naturally I would expect when I applied positive, it was in this direction, the previous slide, right? It was this direction. If I apply A, it is in this direction. Only thing is, I am not reading out the signal. I am reading out the signal just after I switch. So I am starting to read the signal from here, left to right. I have moved here, I am reading from left to right. I am not reading while A is on. I am reading only with B. So I moved it to the left, so I can, when I start to acquire the data now, the data will start from negative U axis and go all the way up to positive U axis with gamma GX TS as the maximum frequency, right? Fantastic. So now the question is, how do you move in this direction?